Okay, first, I have put up an assignments area. Most of the homework pertaining to the second exam, I've put up solutions. So right by the place where you downloaded the original homework, I've put solutions. And so you can scroll through, not every single one, but most. Okay, and like notice sometimes I'll put a note because the actual solutions from those readings will be on a different date. So like here, for these problems, it's in here because you did problems from that reading on different days. Okay. Solutions. Okay, so just look for solutions through here, and then hopefully today, for sure tomorrow, in the quizzes and exams, I'll start a new folder called Exam 2. And so we had 3 quizzes for this exam, and I'll post a blank version of the quiz and a full solution version of the quiz. Okay? So all good for studying. So just quickly, studying. So first of all, the videos. So when you're reviewing a class video, what do you think about and look for? Do you just listen to what I'm saying, okay? Or are you watching what I'm doing? Or what was I meaning, okay? What should your goal be? Meaning, all right? So we always focused on meaning. Okay, when you're reviewing a solution key, whether that's homework or a quiz solution key, so you're looking at my solution, what are you looking for? What do you look at and what are you thinking about when you're reading through the solution key? Yeah?
What specific parts you put in the answer? Like, for example, like bit by bit or accumulation.
Okay. So, are you looking for what I said? Are you looking for why I said what I said when I wrote? Or how did I decide to do that? Something to think about. How do you study? So you're looking at, so now you tried it yourself, and now you're looking at the real solution. What is it you're looking for in order to improve your thinking? Okay. Why is important. Okay. Why did I write what I wrote? Okay. And then for sure, so this is the key. How did I decide? Okay? How did I decide to write that? What was happening? So here's a kind of breakdown of that. What ideas am I drawing upon in the solution? What connections am I making of these? This whole semester we've been all these building blocks, and many of these problems draw upon different things. The coherence of ideas. Okay? How did I understand the problem? These are the kinds of questions you want to ask yourself as you're reviewing and trying to fine-tune your thinking and understanding of things as you're reviewing solution keys. Okay, any questions about that? Because I don't have banks of practice problems, because we know that's not our paradigm here, right? There are lots of questions and problems throughout the homeworks and the quizzes that we want to go back and make sure that we really understand how to make decisions when faced with a new problem. How to make decisions. Okay. So this has been our journey so far. Accumulation from rate. And we're actually now turning the corner. All right, so now it's kind of a new beginning here. It's going to be the other way. So how do we get rate from accumulation? How do we get rate from accumulation? So let's kind of walk this out. What have we done so far? We started with exact rate of change. What was our goal in the end? So given exact rate of change, we had an end goal. What was our end goal? Kim? Accumulation function. Was our goal an exact accumulation function or an approximate accumulation? Okay, yeah, so our goal was to get the actual accumulation function, the real one, right? That was our goal. And so we've been on this like month-long, 5-week journey, starting with exact rate of change. How is it that we get to exact accumulation from that? So what was the first general step in our journey, starting with exact rate of change? Jeff?
Adding up the bits and pieces.
Before that even. What did we do before? In order to add up the bits and pieces, did we do that with an exact rate of change function? No, what did we need? Yeah.
Setting up the step function.
Yeah, so Katie said it too. Step function. What is a step function? How does a step function relate to the exact rate of change? Yeah.
It gives us a constant rate for over an interval, so we
Okay.
can kind of estimate what it would be.
That's right. So the step function was constant rates. How did that step function of constant rates then compare to the exact rate of change? Was it exact? No, it was kind of like a model or kind of a simulation of it, right? So from exact rate, we did approximate rate of change. So can you see the steps there? So the steps then, they model or they simulate the exact rate of change, but they leave us with an approximate rate of change graph. Okay. So from that, what did we get from there? What was our goal again? Our goal in the end is, over here, exact or approximate accumulation? Exact accumulation. We want to know what's the real accumulation function. So what was our next step in that goal once we had the approximate rate of change? Joe?
An approximate accumulation function?
An approximate accumulation function, right? We built the approximation, like Jeff said, bit by bit, we built up an approximate accumulation function. What does that look like? So when we graph an approximate accumulation function, when we build it, what kind of function is that in general? I know Kim knows. Savannah, do you remember? Yeah, so, and then, Kim, what were you going to say? Yeah, the line segments glued together, or the piecewise function, right? That's our approximate accumulation function. Each one of those pieces comes from one of the steps, right? Each one comes from a constant rate. Each one of those line segments comes from one of the steps, constant rate. And then from the approximate accumulation, we could get, what could we get? Roman.
An approximate answer for a certain x value.
Okay, so we could use that function and get approximate accumulation. But remember, but in our journey here, what's the next thing we could build from that?
The actual group.
Okay, the actual accumulation, and how do we get it? So what was the key from moving from approximate accumulation to actual accumulation? What allowed us to do that? Nathan?
Is it making the little bits like really small?
Yeah, so changing delta x to like microscopic or atomic distance dx, and that gave us the exact accumulation. Okay, and so having put in all the hard work, we paid our dues, we understood the whole process. That gives us the right just to say, we know this whole process, but given the rate of change function, we've got this very nice compact form, and within 10 seconds, we can write out with the exact accumulation function, knowing the whole meaning of this, right? We did all the hard work. We did all the heavy lifting in between, being able to earn our right to declare that the exact accumulation function. Okay, so then what are we going to do now? We're going to start with an exact accumulation function. It's exactly backwards now. We're going to do the other way. So given an exact accumulation function, how much we have of something, we can approximate it with a linear step function. A linear piecewise function. And then from that linear piecewise function, we can get approximate rate of change function. Where do these rate of changes come from? So if we have the approximate accumulation function, where do the y values, or the constant rates, where are those going to come from? How are we going to get those values? Charles? So these y values of the constant rates, how are we going to get those from the approximate accumulation? From the change in x? Kelvin?
Is it the change in y?
The change in y. Joe?
Change in y over change in x.
Change in y over change in x. Which is it? So what do we have? We have an approximate accumulation function, a piecewise linear function, and from that we want to get rates of change, constant rates of change. How do constant rates of change come from this? Is it delta x, is it delta y, or is it delta y over delta x? What do you think? She wants delta y over delta x. Agree? Mm-hmm. Yeah, because remember, so what was our constant rate of change meant? Changes in y were proportional to changes in x. And what here is the constant rate of change? K. K is that constant ratio that, given the change in x, gives us the change in y. And what does it equal? So how do we get these values, rates of change, off of this graph right here? What is it about that graph that gets us these values? Yeah, well.
Slope of the pieces.
Yeah, so the slope of each piece is delta y over delta x. And those slopes will then form our constant rates. See, that this journey back is going to be a lot easier because we know everything about this journey from here to here. And so just going backwards is going to be a lot easier because all the tools have already been built. Okay? And then how can we, same idea as something before, how can, given this approximate rate of change function, how can we get the exact rate of change function? Janica. So given the approximate rate of change step function, how can we get the exact? Okay, Sam. Saskia.
To get the approximate?
No, we've got the approximate rate of change. And now we want the exact rate of change. Where's that going to come from?
A derivative.
Well, I don't know what that is. So,
With really small intervals.
yeah, so we're going to make the interval small. And we already did this. You know, we had a rate function, where we had the delta x step function, and when we made delta x small, we saw that we got the rate function. So making delta x smaller and smaller means that step function, better and better, approximates the rate of change. So really, really small delta x will mean the exact rate of change function. Like dx, right? So when delta x becomes dx, like the distance from the nucleus of an atom to the electron, then we get the exact rate of change. Okay. And then, same thing. So we want the fast track, right? Given exact accumulation, we want to write down what the exact rate of change is. So if we're starting with exact accumulation function now, where do those come from? What are those? Where do they come from? Where do we find exact accumulation functions? Those are our starting point. Well, you've been working with them your whole career, okay, your whole math career. Let's look at some examples. So, the area of a square function. So if the input is the side length and the output is area. Okay, so in the past we thought of that as a quantity function. You know, the function cranks out some quantity. How can it be thought of as an accumulation function? So the key is, what is accumulation?
The greater the side length, the less
Yeah, it totally has to do with increasing the side length. As you increase the side length, thinking about x increasing. As the side length increases, what happens to the area? It grows. It accumulates little bit by bit. Okay, so any quantity function really can be thought as an accumulation function just by looking at small increases in the input. Then your output's going to grow bit by bit. Okay, so if that area function is an accumulation function, then it can be written this way for some rate of change function, right? Okay, another example is a sphere. So the volume of a sphere depends on what is x in this formula. It's the radius. So how can this volume function be thought of as an accumulation function? Jack.
As x gets greater, the accumulation increases with our factor. We're not going to factor it by
Okay, so yeah, we think about the radius increasing. What happens when the radius increases? If you increase the radius a little bit, you add a little bit of volume. Increase it some more, you add a little bit more volume. Okay, so volume is accumulating as radius increases. So as an accumulation function, then it has to be, or it can be written as accumulation of some rate, or some using its rate of change, right? These are the bits of volume. So any function that gives an exact amount of one quantity as a function of another is an exact accumulation function, therefore it can be represented as an integral of its exact rate of change function. So just a few more examples. So just to show you that it's not, geometry isn't the only thing here. It can be any kind of quantity function. For instance, profit. So profit is, say, the function of the number of units produced and sold. And often profit functions look like this. How can profit be thought of? So profit we just thought of as a quantity. You know, for this number of units, we get this profit. But how can it be thought of as an accumulation function? Jeff?
Because over time, as you sell more units, the profit builds up like bit by bit.
Yeah. So for every unit that we sell, we're going to get a little bit more profit. We're going to get a little bit more profit. Okay? Joe, what were we going to say?
Basically that. Yeah.
Okay. All right, another one is like gallons used in your car, gallons of gasoline, and distance traveled. So maybe that graph might look something like this. Depending on what speed we're going in the car, we get different efficiencies, right? How can the distance traveled be thought of as an accumulation function? Somebody new. How about over on this side? Nicole, how can the distance be thought of as an accumulation function? What's that?
Distance accumulates bit by bit.
Why does it accumulate bit by bit? As what? What causes the distance to accumulate bit by bit in this scenario?
As the x-axis increases.
Yeah, right. So as we burn more gasoline, every time we burn a quarter gallon or a tenth of a gallon, our distance is going to increase a little bit. So more than just a quantity can be thought of as accumulation. So in all these cases then, we can think of it as an accumulation function, but we don't know the rate function. Okay, and this is what we're going to do now. So given this quantity function, think of it as an accumulation function. Devise a way to figure out what the rate is. Okay, so here's the square function. So this is the side length. And this is the area. So if we create a approximate accumulation function, what will that be like? So we want an approximate way of approximating the accumulation that's going to help us get what the rates are as the side length increases. So the side length will be increasing, or what we're after is the rate of change of area. So we're going to start by having an approximate accumulation function that's going to help us nail down some rates. What will that approximate accumulation function be like? Ashlyn, any ideas? We want to build an approximate accumulation function out of this one that's going to help us get some rates of change. What will that function be like? Thinking hard. Any ideas? Will? Okay, break what into pieces? Okay, so if we use, for instance, 1. So if we're going to make a delta x of 1, what's the approximate accumulation function going to be like? Is there another, Calvin?
Could you set like you can set a rate, a constant rate between that interval.
Okay.
So
Do we decide what that is? Do we decide what the rate is?
could you use like the slope of the graph, or not the slope?
Okay. Slope is important. The question is, what's our approximate accumulation function going to look like? Kim?
Did you take, so the point on the line at 1, and then the point on the line at 0, and the point at 0, and separate that?
Okay. So you're just looking at this point right here, and this point right here, and you want to do what?
I want to find the slope of those 2 points.
And so then what would, so that's, yeah, exactly. Okay, so take this point right here, take this point right here, and let's get the constant rate between those 2 points. And then go to the next delta x interval, and we'll get a new constant rate for that one. And so this is like our piecewise linear function that's approximating the accumulation. But the advantage now is we can nail down a rate of change here from this, right? So now we can say, here's a rate of change for this, where we couldn't before, because the rate is always changing. But now we can say, oh, okay, from 0 to 1, we've at least got some estimate of the rate. See? And then from 1 to 2, we've got kind of an estimate for the rate in that interval. Okay? And so the key is that now we can get constant rates of change. We like those. They're easy to work with, right? Delta y equals k delta x. Okay, and then what can we do to make it better? Nick?
Make delta x smaller.
Make delta x smaller. Do you see now how the new blue lines are fitting the exact accumulation better? But then, what about constant rates? We've got more of them, right? We've got more to figure out. Okay, so what you're going to do is just a little exercise here. So what's the actual, we got a red and a black graph. What's the actual accumulation graph? And what's the approximate? Red or black? Don't fold it. How can you work on it if you fold it? Okay, so what are we doing? We're finding constant rates. Thank you. Constant rates. Is it the red graph or the black graph? Go. You can work together.
Yeah, but the Y is like one. Let's do it to. Yeah.
So the slope there
Yeah, no, So it's 10.04, 0.05. Someone really close. I was talking about the first one.
Yeah, but each interval is the same distance.
No. He's saying they subtract this one from that one.
That doesn't bring you.
Because that's the change.
Yeah, so it doesn't matter. So it's,
You guys put 0.05 or 0.04.
What you guys find is the Y.
No, we're just finding the rates, not the accumulation, so we wouldn't have to minus the rate from the other one.
Yeah, our goal is a rate of change function. So all we want from this are the rates of change. So that's what I want you to find, is the constant rates of change. It's that our goal in the end is a rate of change
But is
function.
that the change in Y?
That's it. You don't need to subtract anything, so it's just
No, because isn't it
Make sense?
the change of y 1, not change of y 2?
Are these the constant rates?
No, well, why would it?
Oh, no,
you
there's
know,
just
start
all the
with
numbers.
two different rates when you've already.
Nice. Okay.
Because it's not
Well, no, it's the change.
Point- 0.16 isn't the rate for the whole interval. It's just
That's the
it's
y.
0.1.
0.16 is the
Point-
y for that. So
Yeah, but 0.11 change. I mean,
Yeah, you bet.
oh,
oh, does that make
I get what you're saying.
Okay.
Yeah, after the exam 2, then you'll have a good. So
I
your
agree.
exam and your quiz average is the best indication of your grade.
I totally, it made sense to me on the X part for the Y, just took me a little bit to
Just to look again, but I'm guessing like all your whole quiz average this semester is like 1 or 1.5.
Yeah.
But after particularly second exam,
0.35.
if you want like a really solid or exact value, you can come in and see me. But just a rough estimate of your exam average.
0.35 minus 0.16. 1.19. Just leave my fraction.
That one is,
And then the next one at 0.8 is 0.6 minus 0.35. Alright, and then the one after that is at 1. So it's 0.4 over 0.2. Nope, fuck. That one, 0.8. Okay, it's 0.65.
Okay, Isabel. So I want this third one from here to here, right there. Help me find that one.
So from the point at point 4,
Okay?
looks like it's about point 4 and point 1.5.
You're saying the y value is 0.15?
And then point 2 over at point 6, the value looks like point 6 and the y value point 35.
Okay, good.
So we found the slope for that interval, so it's 0.35 minus 0.15. Delta x. That's why for delta x, yeah. Over 0.2.
And what'd you get?
We got 0.2 and 0.3, so 1.
She said, so this, you guys are all, you're estimating your y values. So you might all get something a little different, but we should all be close. So how about, did you guys get something close to 1 for that third constant rate of change? Any questions on finding these? So let's just get a general profile here of the rate of change. Bailey, what'd you get for the first one? 0.25. Is that close to what the rest of you got? Okay. How about this one? Andrew, what did you get for the second?
Second, I got 2.5.
2.5? So that's a bigger rate of change than this one of 1?
That's wrong.
Yeah, something went wrong there. How about Joe?
for the second interval.
Second interval.
What I got,
Yes.
0.55.
Close to the rest of you? Okay. Fourth interval. So we got 1 for the third. Sam, fourth interval.
I got 1.5.
1.5. Yutong, agree with that? Yutong, what'd you get for the next one? Didn't do it yet. Anyone get to the fifth interval? Yeah. 1.75? Are these exact rate of change or approximate? Approximate. They're kind of there's two reasons why these are approximate. Why there are two reasons why these are approximate. What's one reason? Yeah, Katie.
Delta X is fairly large.
Okay, so you're talking about actually trying to match the rate of change to the real rate of change. And so for large delta X, we're going to be off because of that. And then there's another reason these are off. Yeah.
Because the y value is not exact.
Yeah, you all are picking off, eyeballing what those y values are. And so you're all going to have slightly different y values, leading to a slightly different approximation. So yeah, so in terms of the idea of approximating the rate of change with large delta X, it's going to be an approximate, but then there's also the added effect of you're all picking off these y values differently. But in general, do you see that this is not a far cry from having a rate of change function? What's the rate of change for these x values about? The rate of change of area with respect to side length. Rate of change around here. So easy it's hard, right? What is it? 0.25. Then as x increases and the square gets bigger, then the rate of change of area about 0.55. Then what? So this is, we're building a function, you see? For different x values of side length, we're building this function of rate of change. Anybody have a question so far? Okay, so let's try this. So now, what if we took away the scale? So now we're going to say we don't know the x-axis scale, nor do we know the y-axis scale. So this is some other quantity, so it can be any quantity now. Okay. And the red graph is our actual accumulation function, y equals f of x. All right, so we've got our delta x interval. But this could be anything. This could be 10, it could be 2, it could be 0.5, it could be 0.01. Okay, any delta x. And I'm going to come along here and I'm going to go, boom, any x value, okay? And what do I want? I want the approximate rate of change, this constant rate of change at the value x. So we're given a delta x. And some input x. What is the constant rate of change? And this is the constant rate of change for the approximating function at x. Okay, so we're going to build a rule that all we need is delta x and the input x, and the rule will spit out what that constant rate of change is. We got 4 minutes. We're going to do it as a team. Can we do it?
Yeah.
And then we'll have 12 break. Okay. Any ideas to get started? You tell.
Is that just r of left of x?
Okay, she's talking about something up left of x. So why do you want to use left of x?
Because we are using the left side interval, and we need
Are the coordinates of this point important for us?
yeah.
And so what's the x coordinate of that point? No, this x could be anywhere, right? That x could be anywhere. Yeah.
Is it 3 delta x?
No, x could be in any interval.
Oh, okay.
Jack.
Did you want to find the change in y first?
I want to know what this x coordinate is.
You can just do x minus delta x. Do some distance.
No, because x minus delta x will put me here. That'll put me here. Yeah, she got it. It's left of x. Okay, so what are the coordinates of that point right there? X coordinate is left of x. Somebody else, what's the y coordinate right there? I'll put it in red. Joe? F of left of x. Because it's on our curve. Does it make sense? So now what do we need next? How are we going to get the rate? Can we get the rate just from this one point? So in general, this rule to calculate the constant rate of change, what will that rule be? Just in a very general sense, what will it be to get the constant rate of change? Nicole? Oh, I thought you were kind of raising your hand. It's the same thing you did on your paper. Okay, and how do we get that? What is that? Delta y over delta x. Do we know any of those off the top? Do either of these known?
Yeah, we're given delta.
Given delta x. So all we got left is delta y. So how are we going to get delta y? We got the y coordinate of this point. Roman.
Would it be f of x minus f of left of x?
What's f of x? F of x would be this point. It's a little bit lower than the point on the constant rate. Do you see that? So f of x is down here. So it's not quite right. We're going to need a change in y. Yeah, Kelvin. Okay, the right is here, but we don't need to use the right side function. How can we get the coordinates of that point? We could do right of x, but left of x plus delta x. So, in red, what's the y coordinate then of the second point? Ashlyn. Go ahead. Nick. That's it. That's that right there. So, what's the change in y for this interval, delta x? Connor.
Is it the left of x plus delta x?
Nope, we need the change in y from here to here. And this change in y right there. Joe.
F of left of x plus delta x minus f of left of x.
You see? It's the y coordinate at the end of the interval, which is f of left of x plus delta x, minus the y coordinate at the beginning of the interval, which is f of left of x. So given any delta x and picking any x coordinate anywhere, that will get us this approximating rate of change of the constant rate in that interval. Okay, this is the last, this new stuff is on the exam, so there will be homework for Wednesday, but then most of your time spent will be getting ready for the exam over break. So you don't have, there's no recitation today, and then I will see you Wednesday, next time. See you Wednesday. Have a great break.
Could you say that these are proportional to each
Let me just turn this off. Or what proportional?
What we were talking about earlier in the class.